Welcome to Comp 19512. In the series Introduction to Computer Systems, we're going to look at lectures 5 and 6, and in that we're going to look at systems, particularly computer systems, and a very simple one. We're going to introduce the concept of a little man computer as a model of a real computer. Then we're going to look at what you need to program that little man computer, its instructions, and we're going to write a very simple program. At the end we're going to see you can actually run this program and sequence through the program itself on paper. So before we do that, let's undertake Q1 and look back at our previous lecture and undertake this process of adding two binary numbers. So remember, here we're adding an 8-bit number to another 8-bit number, and to validate and check your result you can also add these decimal numbers afterwards to validate that you've got the correct binary result. So if I leave you to think about that for a few minutes, or seconds in fact. Now let's look how you do this. Well, you write down the top number on the top line, and then you write down the second number under it. Remember, you're adding the two numbers. Then below that second number you draw a line. Below this is the summation row. Then below that you write another line, and then below that is the carry line. So in each column then you're going to add two digits together, form the sum here, and the carry then moves over to the next column. So let's do this starting at the least significant bit. 1 and 1 in counting in binary is 1, 0. So we carry over the 1, write the 0 down here. And then we add the next column. 0 and 0 is 0. Add the carry in, 1. Move to the next column. 0 and 0 is 0. No carry. Move to the next column. 0 and 1 is 1. Next column. 1 and 0 is 1. Next column. 0 and 0, write the 0 down here. Next column. 0 and 1 is 1 written down here. Next column, final column. 0 and 0 is 0. So the resultant 8-bit number is 0, 1, 0, 1, 1, 0, 1, 0. We can check this, and if you want, by dividing by 2 as you've seen in the previous lectures, and the answer is actually decimal 90, which that number represents. Now let's move on to talking about this analogy to a real computer. This concept of a little man computer. We'll see what it means. So let's look at our learning objectives for this lecture. What should we get out of this lecture? What should we understand? What should we be able to write and read? What should we be able to comprehend at the end of this? So, what we should really understand at the end of this is the organisation. What's in the little man computer? Where is it? What components are in it? So we're going to understand the basic organisation of the little man computer. And then after that, we're going to look at the instructions in this little man computer so we can write and run a program. And there actually is a simulator for this that if you've got a PC you can run. And then during that process we're going to explain the difference between machine understandable instructions, machine language, and human understandable assembly language. So we've looked at here the difference in understanding, writing, running and explaining, and we're going to understand the components of a little man, how to write a simple and run a simple program, and the difference between assembly and machine language. So, what is this thing? It's a hypothetical, a virtual, a model of a real computer. And it's got some features, and they're key features that align directly with a real computer. So what we're going to do now is we're going to explicitly explain the relationship between the processor executing these sets of instructions, and a bit later on we'll show you how they're fetched from memory, or the analogy to memory. First thing to realise is this was developed in the 1960s, the middle of the 60s, by Dr. Stuart Madnick in MIT. So what is it? Well, it's a simulator. It's a model of a program that you can write instructions in and process data. So here it is. This is the little man in a walled room. Outside, the boundary of this area is a walled room. The little man here processes information. He doesn't actually throw them on the floor like this, but what he has to do is deal with these sheets of paper and move them around the walled room. So what's in this room? Well, first, this is the little man who's the only thing that moves in the little man computer walled room. How does he get the data in? Well, this is an iconic basket. Now the little man will remove data from here and place it somewhere else, but an external entity will move it into here. An external entity has the ability to place sheets into here, but remember, if there's a sheet already here that this little man hasn't removed, it will overwrite them. So this one is called the in basket. An external entity places data into the in basket. And the other one that lets the little man move data out of this little man computer walled room is the out basket. He moves the little sheet of paper into here, and an external entity will pick it up and move it out. So that is the out basket. Where do we move these data items from and to get them into these two containers? Well, we move them from and to this thing. This is a calculator. So in this model, every piece of paper that's moved either out or in will go via this calculator. To move data out, you must place it first in the calculator and then in the out basket. To move data in, it's placed first by the external entity in the in basket and then moved into the calculator. So how do we process data then? Well, this is a calculator. It's actually a single 3-digit register. It does perform some very basic algebra manipulations, and that's because it's an arithmetic logic unit. It performs add and subtract. We're going to tell you about some prerequisites when you do that a bit later on. So where do we store the data? Now this is very profound. Old-fashioned computers used to run the data outside this model and process cards or run through tape. Then this amazing idea of bringing the information inside the computer and storing it somewhere and putting it next to the arithmetic unit here, so it can be very fast. So what are these two columns? Well, these are the mailboxes, made up of two constituent different parts. One is the mailbox address, 0 to 99, there's 100 locations, and one is a sheet of paper, one of these, that's placed in the mailbox, which will have 3 digits on. So now we can see that we can move information in from the in basket to the calculator, and we can also move it from here to a location in a mailbox. And the program is sequenced. How do we sequence through a program? Is this the program? Well, we do it. By the way, this is called a stored program. So it's not an external piece of tape which holds the program. It's internal, hence it's called the stored program concept. Now the way the program is sequenced through is using this device. This is a counter that tells us the next address of the next instruction. So here, this counter is pointing at that location, and it points at this sheet of paper which would have to be decoded to find out what to do for this instruction. And this is called a program counter. The program counter points at the next instruction. So how do we start off this whole program, this sequence of instructions held in the locations of these addresses, of these mailboxes? Well, we do that with a physical thing that the external entity presses, and that's called a reset button. When we press this button, it resets this to 0, and we start at this address. So to start a program, there's no instruction to do it. We press, an external entity presses the reset, and then the little man sequences through a sequence of instructions which we're going to see in a minute. So that is the little man computer in a walled room, inputs data in the in basket, then can move it to the calculator, then we can move from the calculator to the mailboxes, and then the data can be moved from a mailbox location to the calculator to the outbox. Implicitly this could be the data. Implicitly, as the program counter is pointing at, this could be the sequence of instructions that the program will follow to process the data. Let's move on now. This is of course the reset button that starts the whole process at the correct base address 00, and this is a sheet of paper in that location. Now we'll move on. So we've seen that the mailbox and the input and output mail baskets, calculator, program counter, reset and the little man himself make up the 7 items of a little man computer. Well, he's working in this walled room on his own. He's the only one that can move around. What he tends to do is move in information or communicate with the outside world via these in and out baskets. So if he's bringing in information, it comes in via the in basket. If he's moving out information, which is slips of paper, he moves it out of the out basket. So all the little man can do then, and it's the only object that moves in the little room, is do this. And that is, he controls everything in the room. Well, not quite true. Nearly true. He actually is told what to do, and he follows what the program counter points at as an address in the mailboxes, and then he decodes each instruction, and he must really follow what that instruction does. So we'll see more about that in the following slides. There are a number of objects which we can see are in this little man computer. So now we're going to look at each one and explain them in a bit more detail. The first two are means of getting data in to the little room or out. One of them is called the in basket. A sheet of paper is placed in it by an external entity. And the other one's called the out basket. The little man will place it into the out basket, and the external entity will remove it. So here's a basket. This basket represents an in basket. The data would flow into it, and then the little man will take it out. So this holds one slip of paper when the external entity has placed it in there. The next thing to realise that on this piece of paper placed in the in basket, there's 3 digits. So here's some examples of the digits that could be placed on that piece of paper. The paper will be placed into the in basket and then moved somewhere else in the walled room. And an external entity will place it in here. Now the out basket, another basket here. The difference is the flow tends to be into it and then out of it. This is the same as the in basket, but the little man tends to place data in, which an external entity will remove from the out basket. And then the external entity picks it up and removes it from the walled room. So let's look at these mailbox. Pretty amazing concepts, these. There's 2 columns. One is the address, the location of the mailbox, and the other is the actual location of that address, and the slip of paper is represented here as 3 digits. There's a slip of paper in this one, a slip of paper in this one, and this one and this one. The 3 digits in this one represents 500. So let's talk a bit more about mailboxes. There's 100 of them, 0 to 99. Each one holds, at a specific address, 0 in this case, 3 digits on a slip of paper. So there's 3 digits here on each slip of paper. Remember, these won't be nominally here all the time. These slips of paper are placed there. So the little man is instructed to place these pieces of paper into mailbox locations. And if there's a slip of paper already in there, it will overwrite it with a new piece of paper when it moves it on top of it. It's actually destroying it. Now this really happens in RAM and ROM, read-only memory and random access. So when you move a variable to a specific address in memory, you overwrite it, you destroy it. So the new data overwrites the old, and the old data is explicitly lost. So let's look at this in a bit more detail. So we've got 2 numbers associated with a mailbox. The first one on the left is the mailbox number or address. Specifies an address in a particular location. This address, in this case, is address of mailbox 00. The other item in a mailbox is the mailbox content, which we can view as data, which we don't know yet is either an instruction or real data that the instruction is going to process. 3-digit code on a piece of paper is the data. That's the content. Now we move on to think about more items in the little room, which is the little man computer. The first one is the calculator. What does it do? And the next one after that is the program counter. The calculator is a very, very simple pocket calculator. It can only store 3 digits. It can only do add and subtract, load and store. So we move in data into it from the in basket or from the mailboxes, and then if we do an add or subtract, we must remember something first, and I'll tell you about that prerequisite condition in a minute when we deal with those instructions. So this calculator can be loaded into or stored into, loaded from to or stored from, and it can be added to or subtracted from. Now the program counter is used as a way to tell the little man where to go to next in the mailbox. In this case, it would be the next instruction is at location mailbox address 3. So it will go to the mailbox address 3 and pick up that piece of paper. And the program counter explicitly holds the address of the next instruction, the next slip of paper, which the little man is going to process. Probably, in this case, it will be the next instruction in the program. Now, to start the whole process off, there's an external button which is only pressable by an external entity that resets the whole process. It sets the program counter 0 to 0 and points at, once it's been set at and press this reset button, the mailbox address 0. So we would start executing from this address once the mailbox and after the reset button has been pressed. So what does this little man do in the little man computer? Well, he follows these 6 steps. In a short while we show you one of them he repeats in a subsequence of 3, but we'll just talk about the overall 6 steps first. And he always does this. He constantly, for his whole time, repeats these steps. What are they? Well, the little man goes through these steps. Let's follow what he does then. First he reads the program counter, and this tells him explicitly where to go to, the address of the next mailbox for the next instruction, which he has to obey. And here we are. The little man looks at, and we're starting off a program here, the program counter which has got the address of the first instruction, and it's at mailbox address 00. So each time the little man reads the program counter, 1 is added to it. So after he's read this program counter, it will be indexed or accumulate a 1 into it or added to it, so this would then go to 01 for the address of the next instruction. So what does he do next? Well, once he's got the slip of paper which the program counter points at from the specified mailbox, in this case mailbox address 0, that's what he does. He goes to the mailbox, to the specific address the program points at, and gets the slip of paper. So that's step 2. When he's told to, he goes to address 00 and picks up the slip of paper that has 500, 3 digits on it, base 10. So the next thing he does is he reads the slip of paper, the 3 digits, which is coded into it, the instruction, the process he has to undertake for this instruction. So in this case, he goes and picks up the slip of paper and he decodes it to find out what it does. He reads it, and he must obey this instruction. Once he's done that, which is actually fetch the instruction, he decodes it. He looks at part of this 3 digits and works out what this instruction means he has to do. What does he have to do, and where does he have to move maybe a sheet of paper? So in this case, this is decoded, the 500, to in. Move a sheet of paper from the in basket to the calculator. Then he obeys us and physically does this operation. And then, which is moving a sheet of paper from the in basket to the calculator. Then what he does, he repeats this forever, all the time, 1 to 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, until a halt is called or a coffee break, and then he stops moving the sheets of paper around and stops going to the program counter. So that's what he does. He does what he's told. So now you would have a break in the lecture. Let's carry on. So in the second half of the lecture, we're going to look at instructions and a very simple program with relation to the little man computer. So the learning objectives for this second half of the lecture is we should understand what a basic instruction is, and then in fact there's sets of instructions, we're going to look at explicitly 7, that the little man has to obey. And that's with reference to our simple computer model. And then we look at how we put these instructions in order, one after the other, to write a program, and then we can run this in a simple program of a simulator of a little man. So we've seen we're going to understand, write and run things, and the content we're talking about there is instructions, sets of instructions, and a simple program. So the first thing we're going to look at then is how, on this sheet of paper, do these 3 digits encode to mean something. What does each one mean? So they're laid out like this. The first digit on the left, the most significant digit, means this. It's the most significant digit. It's the instruction code, sometimes in short called the operation code, the op code, and this instruction 1 means instruction, implicit to us as humans, load. A computer would understand 1 and set up to do the correct instruction. Now the next 2 digits, these 2, may be part of this instruction where necessary, they're not always, and they're 2 digits, 2 least significant digits, that when required could be a mailbox address. Some of the instructions do not need these 2 digits and they're just ignored. A lot of them, load and store, do. This one, as it's a load, needs to know where to load from into the calculator, and the address and the mailbox to load from is 37. So this instruction goes to mailbox 37, takes the value on the slip of paper at that mailbox address, and moves that slip of paper into the calculator, copies it into the calculator, and the data on that sheet of paper is 002. After the instruction, 002 is placed in the register in the calculator. Now let's look at these simple instructions one at a time. We're going to look at the first 2, load and store. Load is machine understandable numeric value 1 and human understandable LAD. LDA. For load. And then XX will be the mailbox address we're moving the data from to the calculator. So specifically the little man goes to the address specified here and then picks up the piece of paper, copies the data from the slip of paper held on it in that mailbox address into the calculator register. So that's the load instruction. The machine thinks it's 1. We write it when we write programs as LDA. Now the inverse of that is, well, let's first see what happens. In this case, we're moving data from mailbox address here, so this would be 0, and we're moving it into the calculator. So XX in this case would be 0. Let's look at the store. The numeric value the machine understands 2. The one for us to understand, the human understandable mnemonic or short form, is STA. So what this does is it stores the information from the calculator and moves it to a mailbox. The little man takes the data displayed on the calculator, writes it on a slip of paper, the 3 digits, and places the slip of paper at this address. Let's have a look at what it is visually. So the calculator holds 3 digits. The little man writes it on a piece of paper, places it at this address specified by XX. XX in this case is 00. So that's load and store. Now we're going to look at the instructions add and subtract. These both need prerequisites. What does that mean? It means before you perform an add or a subtract, you must remember to do something. You can't add B to nothing. You must add A plus B. A must be loaded into the calculator first, before the add instruction is undertaken. So the add instruction, numerically 3, human understandable mnemonic ADD, means that we add to the calculator from the address mailbox XX the data in it. So we're adding A to B, where B has to be retrieved from a specific address in the mailboxes. So let's go through it again. Little man goes to a specific address and adds that address to the calculator. So let's visualize it. Here we are. We're going to add this item 300, which we probably wouldn't do, but I'll tell you why later. We're going to add it to the calculator. There must be A in the calculator and call this B. So previously the calculator must be loaded by the previous number if we're adding A and B. This is significantly viewed as B. Now if we're subtracting from the calculator, again prerequisite, we must have loaded A into the calculator to subtract B. B is held at a mailbox address. So this is the numeric value the machine understands. We understand the subtract as SUB. So let's visualize it then. Visually we're subtracting 400. We're subtracting from the calculator this item. We probably wouldn't do this. You'll see in a minute why. So what we do then is we subtract it from the calculator. So let's go through this one more time. Little man goes to a specific address in the mailbox and subtracts the data on the slip of paper from the data held in the calculator. And then we'll have a resultant in the calculator after the instruction has been executed. Now we'll look at the next two instructions, in and out. Moving data from the calculator from the in basket to the calculator is in, numerically 5, and mnemonic in. And in this case, the little man goes to the in basket, picks up and reads the little sheet of paper with the 3 digits on, and then copies it to the numbers in the register in the calculator. So let's visualize that then. So here's the in basket. So the little man picks up a sheet of paper and moves it to the calculator, where he copies it into the 3-digit register in the calculator. Now out, the inverse of this, numerically 6, which the machine understands. For us, our short form for writing programs is OUT. What does he do? Well, in this case, he copies it onto a sheet of paper, the 3 digits in the register in the calculator, and then he moves that sheet of paper and places it in the out basket. Let's see him doing that then. The sheet of paper is copied from the 3 digits in the calculator, and then it's moved to the out basket and placed in the out basket, where an external entity can remove it. Now we're nearly there. This is the last instruction. It means stop. 7 is the numeric value that the machine understands. HLT or COB, halt or coffee break, means the end of the program. So what this means is, when the little man perceives or picks up an instruction 7XX, it means the little man will stop, has a cup of coffee, the program has ended. If we need to restart, we must physically press the reset button, which will reset the program counter to 0. There's no operation code to do this. So here are all the instructions, 3 columns. 1 column is the instructions, which we'd understand, and then there's the opcode the machine would understand, then the short forms, the mnemonics, which we write when we write a program. So let's go through them. Load, store, add, subtract, in, out, halt. 1, 2, 3, 4, 5, 6, 7. Short form of those is LDA, STA, ADD, SUB, IN, OUT, HLT or COB. So here you could write down to try and remember these. LSA, SIOH or 1, 2, 3, 4, 5, 6, 7. Or in long form, load, store, add, subtract, in, out, halt. So you need those to do any of the questions, either the short or the long in the exam, but they enable you to program the little machine. So now we're going to do that. We're going to look at a program as if we were the little man computer, which looks at numeric opcodes. Where are they placed? Well, they're placed sequentially in the mailbox addresses. The first instruction to be undertaken is placed in mailbox address 0, the second in mailbox 1, and so on. So these are the mailbox numbers. Then we place these opcodes, the instructions that the machine understands, sequentially into those addresses. Let's do that now. So we see we've got a set of instructions that the machine will follow. These are the opcodes or values stored on the piece of paper, which will probably be stored when they're moved into the mailboxes at address 0 to address 8. So if we're asked an exam to explain what's happening given this numeric opcode, what we'd actually expect to get full marks is to go back here and explain each one of these instructions in full. So explain all of this in full would get you full marks. But what we're going to do quickly here in this lecture is just go through and say we're going to quickly write a very brief comment. We might not get full marks in an exam for this. So let's go and see them. So here's all the comments, and it says this instructions means input from the in basket. This instruction means store that data then in address in the mailbox 10, and then input again, and then store at address mailbox 11, then input again, then add Now be very careful if you thought this program was doing something like add A plus B plus C, because it's not. It's bringing in A and storing it at mailbox 10, bring in B and storing it in mailbox 11. Then it brings in C, and then it adds C to A. So it's adding A and C, and then the result of that to B, not A plus B plus C. So be very careful when you're scanning the instructions to really understand what it's doing. It is not, and I'm going to say this again, it is not adding A plus B plus C. Look at what it's doing when you read the code. I'll explain that and expound that again later on. So these are the basic comments which wouldn't get you full marks in an exam to explain what's happening. So this is the simulator then. If you want to run it and see a video of it running, go to YouTube. You could run this on your iPad. You can't run the simulator on your Apple, only on a PC. And this is what it will look like. So let's explain what happens, which you can see all this in detail in the real-time video on YouTube. First you load in your program here as mnemonics. Then you get the opcode and it's assembled into here, and these opcodes are numeric. And then you load, you press this button, you move the code from here, the opcodes, into here. Implicitly it will load this first opcode number, 3-digit number, into the first mailbox, and then continue loading sequentially downwards. And then you can run the program, either single stepping or execute the program all at once. And then if you've got to input data, you select here and input data here. To view the output, you look at this. To reset the program counter, it's called here the hand counter, you press this button to start the program again. So this simulator will step you through the program. We're not going to use it here. You can see how it works in this video. Remember to watch it. Now what we're going to do is say, what did that program do? Well, briefly, it reads 3 numbers from the in basket, adds them together, and then sends the resultant to the out basket. Well, how is it doing that? What is the little man actually doing? Well, what he's doing is every time he first has to go to the program counter to get the first address of the next instruction. If the reset button has been pressed, that will be 0. Once he's read it, the program counter, that program counter is indexed by 1, so now it will hold 0, 1, the next instruction address, and that will be the next instruction in the sequence which the little man will follow after this one. Well, let's think about what he does when he executes a program. He's basically going to follow a sequence. As well as following those 6 steps, underneath one of those steps he's going to do this sequence. So he does and undertakes 3 processes or steps. He fetches the data, he decodes the data, and he executes it. What we're talking about here is he fetches a piece of paper. He then looks at the 3 digits, one of them will tell him what to execute. So let's go and do this. So he fetches the instruction from the mailbox. What he actually fetches is the mailbox. What he actually reads is the 3 digits. So then he decodes it. So he has to work out which of the 3 digits he decodes to work out what operation. And as you remember, it's the first digit, the most significant. And then he executes and obeys that instruction. What he actually does is he moves the sheet of paper from and to a location, which he's told to do. Okay, so that's the basic 3 steps he follows underneath those 6 steps we've seen earlier. Fetch, decode, execute. Okay, and then he hits a halt or a coffee break and he stops. So, what is a program then? Well, it's a list, it's a sequence, it's one instruction under another. It's one instruction which it obeys, then the next one is the line below it. So it's a sequence of instructions. So the program counter maybe is the most important thing here. Implicitly, the program counter is pointing at, or should be, the next instruction. It's actually pointing at a location in the mailbox where the next sheet is with 3 digits on, which has to be decoded to find out what the next instruction is. Now at the moment we've seen that we can't change the order. What the program counter is doing in execution order is it's going 0, 1, 2, 3. So far we can't change it. We'll see maybe if you do some research you actually could, but we're not doing it in this introduction. So the mailboxes hold slips of paper. On those slips of paper are 3 digits. Now sometimes those 3 digits via the use of the program counter are interpreted as instructions. Other times they're interpreted as data. Okay, and you might have to go to the in basket to get the data and put it in the mailbox. Or you might have to get the data from the mailbox and place it through the calculator into the out basket. So the only difference that you've got to remember is the mailboxes just don't really know. They've got no sense of comprehension of self. They just store a piece of paper. They don't know if it's data or instructions. Really, the little man doesn't either. He just picks up what he's told and expects it to be an instruction which he's going to fetch, decode and execute. So be aware of this. You could make a lot of mistakes here. So the next thing to be aware of is that program counter reaches a point where in part of the mailboxes we could have moved from the program to the data. So the data must always be placed after the program. We're going to see, if you read these notes carefully, that if you look, you'll see that one of the programs is wrong and we'll be writing data into the area where the instructions are. So have a look later on in these notes and find out where that is and try and explain what's happening. So data and instructions, you could get them mixed up. They should be in the right order. They should start at 0 and then sequence from 0. You shouldn't put the data and write it over an instruction. There should be a bounds to where the instructions start and stop. Then after that, you can place the data. Okay? So we should note now that the mailboxes retain pieces of paper. Some of them, due to the implicit pointing of a program counter, the little man obeys. At the moment it's just sufficient to know how does that sequence of instructions get into the mailbox. But it does. We're going to say, not clear at the moment, but somehow we move them into it in the right sequence. Okay, we'll just hold off on that until a bit later. Now what we're going to do is do a mapping, a relationship, an association between an actual physical computer hardware and the little man. So we're going to associate the little man to computer hardware. First we're going to start with 3 components that make up a processor. The little man computer, the calculator and the program counter. Basically analogous to a processor. Subscript tells you which of the items of a little man we've just talked about. We've talked about 3, 1, 5 and 6. Now the in and out basket 2 and 3 are analogous to input and output mechanisms in a real computer. Whereas 4, the mailbox, is really the primary memory. We'll talk more about that later in the course. Now this primary memory stores numeric values and can be interpreted maybe as instructions or data. So the primary memory is a storage location with a unique address, and at that address you can place a sheet of paper or retrieve one. And this maps directly the final entity, entity 7, the reset button, maps to a physical entity on your computer. You can press a button to restart it and reset it. Now let's think about this idea of instructions. We're going to talk about the ones that humans use, which are an interpretation of the long form to a short form, a mnemonic, a short form. So when writing a program, the machine would like to interpret numeric data. It would probably like, and it would, binary. We're going to talk about it numerically as 3 digits of decimal. So this is called machine language, which is the opcode, which we saw previously in the simulator. We took the mnemonics, we did something to them, and then we got the numeric value, which was the opcodes, which we then moved into the mailboxes in a sequential order starting at address 0, the base address. So the instruction mnemonics provide a means of us humans writing code that we understand, whereas we want to encode it to machine understandable numeric instructions. So to do this encoding from human to machine, from textual language to numbers, we use an assembler that does the transformation, does the conversion. So, an assembly language is what we write as humans, and then it's converted via an assembler to the equivalent machine numerical program language called opcodes. So the assembler is used to undertake this transform. And you can use the simulator at this address if you've got a PC, or you've got to load in a PC emulator into your Apple. So now we're going to think about programs loaded into sequential addresses in mailboxes as if we're really going to probe them. So let's talk about some things you should know. First, the thing I've never talked about is delimiters. This semicolon tells us you could actually put, if you want, comments over here, and it says this is the instruction. After this, ignore the rest. It's going to be comments until the next line when it's going to be the mnemonic, and if required, a number representing the requirement for this mnemonic where it's going to place it, store the data. So let's go back again. So assembly language is placed in sequential addresses in the mailboxes starting from address 0. Each instruction is placed on top of each other. So this is the first, this is the second. It will run through this way. So again, this performs a program. It brings in 1, 2, 3 bits of data. Stores 2 of them in mailbox locations 10 and mailbox locations 11. Then it starts adding them together. But be careful the order that they add them together. It's not adding A, B and C. It inputs A, stores it in 10, inputs B, stores it in 11, then inputs C, and then adds C to A, and then the resultant to B. So it's not adding A, B and C. Be aware you need to read the program to understand exactly what it's doing. Then the result of that is output to the out basket here. Again, you can simulate this, copy it in or type it into the simulator here. So this is assembly language which humans normally write. We write this. So now we're not going to do that. You can actually run these programs and write them on a piece of paper. How would you do that? Well, you lay out a number of columns. You would have an address for each instruction, the opcode, the numeric value for it, which the computer would understand, and the textual representation, the short form numeric, which we would understand. And then any of the data items, mailbox addresses, are viewed as columns. So we're going to store data in these, and if we use a calculator, which we always do, we have a column for the calculator, and the in and out I'm going to leave you to fill in the appropriate time. First, remember, if there's no data in any of these, so maybe you should have these here if required, you have a dash. In an exam, if you haven't got a dash, you could be marked down. You will be, in fact. So let's go through these columns sequentially, explain how you run a program and simulate it by hand on a piece of paper. First, the mailbox addresses are sequential. This program is going to take up maybe 8 or 9 addresses from 0 to 008. So that's the addresses of the mailbox in column 1. Then we move to column 2. This is the numeric instruction that the machine will understand. 3 digits. First one's the opcode. Next, if required, sometimes they're not required, here and here. These ones require addresses to move the data around. Okay. Now we go to the mnemonics. Now we'll understand what's happening in the program because we can read it as a text item. Here's the mnemonics. Remember, this semicolon is a delimiter that says this is the end of the instruction. After this we're going to ignore it, and that's where we can write, if required, any comments. So what's happening here? Well, we're going to input x, y and z. The numeric values we're going to input in a simulator for x, y and z are 2, 3 and 4. So remember what happens when this program is sequenced through. Where does the data come from and go to at the end? Let's go through it then. First, input. Explicitly it's inputting data x, so it's inputting 2. Where is that placed? Well, think about it. Now, where does it go to after the in instruction? Well, it's moved to the calculator. Next instruction, store 10. Move the information at the calculator to mailbox address 10. Let's do that then. So 2 is still written there, so if you don't write the 2, if you leave this blank, you will get reduced marks. Blank means there's no data. 2 is what is in the calculator. And then we move it to mailbox address 10. So let's show that in an arrow. We move the data from the calculator to the mailbox, store it in mailbox address 10. Then we input y, which is 3, into the calculator from, well, you're going to have to fill this in, and move it into the calculator here. So remember to fill in these two here. If it's no data out, put dashes. If the data's in, or there's an in instruction, write it down here. You've got to do that. Now the data is moved from the calculator in the next instruction after the in. So at the moment, remember, let's go back a step, the 2 has not been overwritten. There's no instruction overwriting 2, so 2 must be written down here. If you leave a blank, you will get marked down. 2 is in the mailbox, remember. Now the next instruction is store A, that means move the data in the calculator 3. Before we do that, remember you should write down all the 2's now, because if you look here, there's no other store to 10, so just write down all the 2's. Mailbox 10 has 2 written in it, and it's first written here, and then it stays there. It stores the number 2 throughout the program. Now we're going to see what happens when we do an undertaken instruction that says store A. So it takes the information from the calculator and moves it to mailbox 11. Let's indicate that with an arrow. Moves the data from the calculator to mailbox address 11. Now the next instruction brings in Z. Remember Z is 4. So now the 3 is going to be overwritten. Remember you're going to have to write something here somewhere. Remember to do that, otherwise you get marked down in an exam. So what you've got here is 4 is overwritten on top of 3. So that's the in. And remember now, as there's going to probably be no overwriting of mailbox 11, this, remember to write down all the 3's. If these are left blank or you put dashes, that is wrong. 3 has been loaded into the mailbox 11 here, and it stays there. Now what happens to these 4 steps? Well, first thing that happens is that add is undertaken. The calculator is added to, and it's added to with the data in mailbox address 10. So 4 has added to it the data in mailbox 10, so as you can guess, 6 now overwrites the calculator and is the sum of 4 plus 2. Now we add mailbox 11 to that 6, so it's 6 plus 3, as you'd expect. 9 becomes the aggregate of those, which is 6 plus 3. Then we move the out, this 9 to the out. So I'll leave you to write that down. But remember, as nothing is coming into the calculator or overwriting it, 9 will be continuously rewritten underneath. If you put blanks or dashes, you're wrong. So that's how we undertake and sequence through a program manually on a piece of paper. This is something that is always in exams. Probably worth you understanding how to do this. Now, how do we load the program? How do we get the data into the mailbox? Well, we need to place these sequence of instructions in the right mailbox location. The first instruction needs to be placed in mailbox address 0. The second in mailbox address 01, and so on. So we need to place the slips of paper which perform the sequence of instructions in the right location in the little man computer. So practically, how is this done? Well, it's done by loading into the primary memory in a physical computer from maybe a secondary memory, from a back-end memory. And then we can run the program from a particular memory address. In the little man computer, we run it from 0. So what could we call this thing that does this moving of data, which is sequence of instructions? Well, it's actually called a loader, and it's part of the operating system that runs when you're required to load a program from the back-end store, the secondary memory, into the front-end store, the primary memory. A loader performs this task. Now, to do this, we need to bootstrap this loader to start off. So this means when the power's turned on, the computer goes to a ROM, which we'll talk about here, and the bootstrapping program is held in memory, which is probably in a read-only memory. So when the power's turned on, the bootstrapping program starts and loads in the memory. Now, this is exactly what happens in a real computer, but probably what would happen, the bootstrapping program called a BIOS, Basic Input Output Program, will boot up, bootstrap the operating system into memory, and then hand over so the operating system is now in control. The bootstrapper loads the loader, which will then load the program in our case. So, in terms of the little man computer, we've written instructions in order, in sequence, and we've seen that they're moved into the little walled room, and sets of instructions are then followed one after the other, and anomaly after the reset button is pressed to reset the program counter to 0. So these instructions, when sequenced through, would cause the little man to perform a set of tasks, maybe using the in and out baskets and moving slips of paper from and to the mailboxes and the calculator. Maybe one question you should think about that I'll leave you with is this: do we have an instruction that would cause the program to start running from mailbox 0? Now I'm going to undertake a retrospective or a summary of the lectures using mind maps, which were associative topologies, or morphological information, which means we can interact with diagrams, text and words and associate them. So, what's a little man computer? Well, we need to get information into the little man walled room, and we do this with an in basket. Pictorially, visually, this textually is called an in basket. Now, the out basket is where the little man places the information for the external entity to remove it. Pictorially, it's this shape, and it's called an out basket. Now, the calculator is used always to move information into the little man to handle it, or move it out of the out basket. So it's essential in the model of the little man computer. The calculator is used always to move information to and from the in and out baskets and the mailbox. So this is a calculator. Really, it's a 3-digit register which performs very simple arithmetic logic, and it's called an arithmetic logic unit. Add and subtract is all it actually performs. Now, the mailbox there's two different columns, the addresses and the locations at those addresses, which hold slips of paper. These 3 digits iconically represent the numbers written on the bits of paper. So this represents a stored program, internally stored right next to the calculator. Very, very fast program execution due to this location. Right, how do we run a program? This thing, the program counter, points at the next instruction. So this would then sequence through instruction at address 03. How do we start a program? Well, we do that by pressing this button that sets this to 0 and points to the first instruction at this address, and it would load this sheet of paper with 500 on it as the first instruction to sequence through when we run a program. So let's look at it in more detail then. The first thing to realise is this in basket holds a slip of paper. If the little man hasn't removed it and another slip of paper is placed on top of it, it's overwritten and destroyed, just like the memory or the mailbox is. Where is this data always moved to? Well, it's always moved in and out of these baskets, The out basket is if we're moving data out of the walled room. So again, if the little man places it into here, an external entity will pick it up. Now, how do we facilitate moving in and out of these two? Well, we must use the calculator. When we're moving in, it moves to the calculator. When we're moving out, it moves from the calculator. So the calculator is really a 3-digit register that performs two things: add and subtract, load and store. Actually 4. So it calculates, uses its register to store data temporarily, and it has an algorithmic logic unit to perform these two functions. So the stored program then is really a mailbox, again with 2 columns, let's be explicit here, 3 digits in the second column, one of them 2 digits the mailbox address, the second one is the container for each sheet of paper that could be instructions or could be data. And then it's the program counter that has the address, there should be an S here by the way, of the next instruction. And then to start the program, we press this physical button which resets this to 0, that sets the program counter starting here. Now, what does the little man always do? Well, he does what he's told, and he sequences through these steps all the time. So let's have a think about this. First he reads the program counter. Once he's read it, that will be incremented by 1. Then he goes to the mailboxes that he's pointed to by the program counter, picks up and reads the sheet of paper that was in the mailbox, and then decodes the first digit, remember, of 3, then executes that instruction, physically does the move, and then he repeats this forever unless he hits a halt, and then he stops. So let's look at those 3 digits then. 3 digits. Which is which? This one is the operations code, short form opcode, which tells the computer what instruction it is, 1 to 7. These two are the mailbox address that are sometimes used with load and store and add and subtract, not with the other instructions. Now, let's have a look at the instructions. First one is load, numerically 1. Second one is store, numerically 2. Third one is add 3. Fourth one is subtract. Now these will require an address in XXX. The following do not. So input, implicit, it's moving from the in basket to the calculator. Output, by the way, input is 5. Output is 6, implicit again, moving from the calculator to the out basket, no address necessary. Halt is exactly the same. 7 just tells you to stop. Program's finished. Halt. Now let's look at these in a bit more detail then. First, when we undertake a load, it moves the data from a specified XXX, here would be 37, to the calculator. So it's a piece of paper that's moved from here, mailbox address 37, to here, calculator. Now the next one, store, is 2, which would be 237, which will move the data, write it onto a piece of paper and store it in location, mailbox address 37. And if 2 was written here, which it was, it will be placed on a piece of paper and that piece of paper moved into location 37. Now, add will require you to load into the calculator one of the numbers to be added, A, and then you add A plus B. B is in location 337 is the location of the other part of the addition, which will be 2. So we add 2 on the slip of paper here to the calculator. Then we move to subtract. Again, the same prerequisite. We need to have A placed in the calculator before we can subtract B, which is the address given by XX, which in this case is 37. So 2 on the piece of paper stored at address 37 will be subtracted from the calculator. Then 5XX moves data from in to out basket, into the calculator. Output 6XX moves the data, sheet of paper calculated, 3 digits in the calculator are copied onto a sheet of paper and then moved to the out basket. And finally, halt, we stop the process. So what do we do? As well as doing those 6 steps, during one of those 6 steps, we keep doing this. Well, what is this to execute a program? First, number 1, we fetch the data from a mailbox address, pointed to by the program counter. 2, we then decode the most significant digit, 1 to 7, to find out what to do. Then 3, we obey that instruction, we actually execute it, and then we do this again and again, going through top level 6 instructions, but fetch, decode and execute is 3 steps. So now how can we map our little man computer model to a real computer? Well, firstly, the processor maps to the program counter, the little man, and the calculator. Secondly, the in and out basket map to the in and out mechanism of a computer. Then finally, where is the program stored? The programmable memory, which is normally called RAM, is called primary memory. So thank you very much for watching this lecture. I hope you enjoyed it and undertake the questions at the end of the lecture.